A modern fighter jet can have over 1,000 kilograms of rare earth-dependent components. Not the flashy parts people imagine, not the engine blades or the radar dome you see in documentaries. I'm talking about the quiet internals, actuators, guidance systems, magnetic assemblies buried deep inside the airframe. The kind of parts you never see, but without them, the aircraft doesn't move correctly, doesn't aim correctly, doesn't think correctly in a mechanical sense. Now take a step back from that image and you hit something far less cinematic. Neodymium, praseodymium, dysprosium. Elements that most people only hear about when supply chains start breaking. The global system depends on them more than it admits publicly. And yet the striking detail is not where they come from. It's what happens after they are mined. China doesn't just sit on large deposits. That's the shallow reading. The more important fact is this. It controls the midstream processing layer that turns raw ore into usable, high-performance magnets. According to the US Geological Survey data over recent years, China accounts for roughly 85 to 90% of refined rare earth output, and an even higher share in magnet production. That gap between mining and refinement is where the real leverage sits. Here's where the structure becomes uncomfortable for most industrial planners. Mining rare earths is messy, but not technically extraordinary. Australia can do it. The United States can restart it. Brazil, India, Vietnam all have deposits. The bottleneck isn't in the ground, it's in the chemistry. Separating rare earth elements requires solvent extraction at scale. Hundreds, sometimes thousands of stages of chemical baths, each tuned to isolate nearly identical elements from each other. It's slow, environmentally toxic if poorly managed, and capital intensive in a way that doesn't attract fast private investment. China spent decades building that capacity quietly while other countries outsourced it because the margins looked unattractive. And that decision compounds over time. Because once you dominate separation, you don't just control supply, you control refinement standards. You decide what battery grade or magnet grade actually means in practice. You become the default calibrator for the entire global supply chain without ever needing to announce that position. There's a tendency in Western policy circles to talk about rare earths as if they are a mining problem waiting to be solved. That framing misses the operational reality. Even if a new mine opens tomorrow in Texas or Western Australia, the material still has to be shipped into a processing ecosystem that is already structurally concentrated elsewhere. And building a parallel one isn't a 5-year project. It's closer to a decade-long industrial rebuild, assuming political continuity holds, which it rarely does at that timescale. This is where the military dimension quietly enters the picture without needing dramatic language. Systems like the F-35 rely on precision-grade magnets in flight control systems, radar assemblies, and electric actuators. Substituting those materials isn't trivial engineering substitution. It often triggers redesigns of entire subsystems, certification delays, and performance trade-offs that don't show up in procurement summaries, but do show up in readiness rates. And the uncomfortable part is how invisible this dependency remains in normal policy conversation. Because the supply chain doesn't fail loudly, it fails in increments, slightly longer lead times, slightly higher costs, slightly fewer suppliers willing to certify components. Which raises a quieter question that doesn't get asked often enough. At what point does globalized supply chain efficiency stop being efficiency and start becoming structural dependency with no easy exit? We'll pick that up in the next part because the history of how this concentration formed is not accidental, and it didn't happen quickly. There's a habit in industrial history of treating supply chains like they are the natural outcome of comparative advantage. Country A has ore, country B has factories, country C does assembly. It sounds clean on paper, almost elegant, but rare earths never fit that story neatly because the value isn't evenly distributed along the chain. It spikes violently in one narrow segment, separation and refining. China didn't stumble into that segment. It absorbed it during a very specific window in global industrial restructuring, roughly the late 1980s through the 2000s, when Western firms were actively offshoring anything that looked environmentally expensive or politically inconvenient. Rare earth processing sits at the top of that list. The wastewater alone from solvent extraction plants can carry radioactive byproducts depending on the ore source. That makes it politically toxic in jurisdictions where environmental regulation has teeth and election cycles are short. So the early trade-off looked rational. Let China handle the dirty middle. Keep the design, the high-end manufacturing, the branding, the final assembly. That division of labor worked until it didn't. Baotou in Inner Mongolia becomes important here, not because it is unique geologically, but because it became a concentration point for processing infrastructure at scale. Over time, clusters formed: chemical separation plants, magnet manufacturers, downstream alloy producers. Once those clusters exist, they start reinforcing themselves. Engineers move where the jobs are. Suppliers move where the engineers are. Logistics routes harden around them. At that point, even if another country wants to rebuild the same capacity, it isn't just building factories. It is trying to reconstruct an entire ecosystem of tacit knowledge, calibration techniques, waste handling routines, equipment maintenance practices that never make it into textbooks. And this is where most strategic analyses go slightly abstract. They talk about industrial base as if it's a switch you can turn back on. But these systems behave more like sedimentary rock formations. They accumulate layer by layer, and once the structure is set, it resists reshaping. There's also a second layer that often gets ignored. Pricing power doesn't require formal monopoly behavior. If one country controls 85 to 90% of processing capacity, it doesn't need to aggressively manipulate prices. The market already clears through its infrastructure. Buyers adapt to its production rhythms, not the other way around. A quiet example of this showed up during previous rare earth export restrictions in the early 2000s. It wasn't just about scarcity, it was about timing mismatches, delays in approval, quotas that shifted quarterly, administrative friction that made alternative planning more expensive than compliance. Markets respond to friction as much as they respond to outright bans. And while the political narrative often framed those moments as aggressive leverage, the more structurally accurate interpretation is simpler. When a system becomes centralized enough, administrative decisions inside that system start to feel like global events. But there's a counter-argument worth taking seriously. China also bears the environmental and economic cost of this dominance. Rare earth refining is not a clean industry to anchor your domestic supply chain around. It produces waste streams that require constant management, and it locks regions into heavy industrial dependence that other parts of China itself have tried to move away from. So it's not purely strategic control, it's also industrial inertia. Still, inertia at that scale behaves like power, regardless of intent. And this is where the story starts to shift from, how did this happen, into something more uncomfortable. What happens when the rest of the world tries to unwind a system that was never designed to be unwound in the first place? There's a point in any dependency structure where the numbers stop being the most important part of the story. Not because they become irrelevant, but because they start lagging behind behavior. Rare earths are sitting right in that gap right now, where governments publish diversification targets, but procurement teams still quietly route through the same bottlenecks they used 5 years ago. Take dysprosium and terbium. These aren't household names, but they matter disproportionately in high-temperature magnets, the kind used in electric motors that can't afford performance degradation under heat stress. Global demand for these materials has been rising in step with EV production and defense electrification. The International Energy Agency has repeatedly flagged that demand for some heavy rare earths could multiply several times over by 2040 if current electrification trends continue. But demand projections are almost the easy part. Supply reconfiguration is where the friction shows up. Even when alternative sources exist, like Linus in Australia or newer projects in the United States, the issue is not just extraction. It's throughput consistency and downstream certification. Defense contractors in particular don't switch suppliers based on availability alone. They switch based on long qualification cycles, sometimes stretching years, where material behavior is tested under extreme and repeatable conditions. And this is where the system quietly favors incumbency. China's advantage isn't just volume, it's repeatability. When a manufacturer orders magnet-grade material from an established supply chain, they are not just buying chemistry. They are buying predictability in performance across thousands of batches. Replacing that with a fragmented, multi-country supply chain introduces variance, and variance in materials becomes variance in system behavior, something defense systems are designed to minimize at all costs. Now, the counter-argument is straightforward and not unreasonable. Strategic diversification is already underway. The U.S. Department of Defense has funded domestic rare earth initiatives. Stockpiling programs exist, and allied coordination with Australia and Japan has expanded over the past decade. On paper, that looks like de-risking, but here's the tension. These programs often operate in parallel rather than in substitution. They add capacity without removing dependency. So the system becomes dual-tracked, a primary supply chain that is still dominant, and a secondary one that is expensive, smaller, and intermittently used. That structure creates an illusion of resilience. There's another layer that rarely gets discussed in public analysis. Rare earth processing is not just capital intensive. It is knowledge dense in a way that doesn't transfer cleanly through contracts or licensing. Small operational decisions, temperature control and separation stages, reagent purity cycles, waste recycling loops, accumulate into yield differences that only show up at industrial scale. You can't fully simulate that in advance. You learn it by running plants for years. So when policymakers talk about reshoring, the implicit assumption is that industrial capability is modular. But in reality, it behaves more like an apprenticeship system embedded in infrastructure. You don't just build it, you stabilize it through repetition. And while that stabilization is happening elsewhere, global demand is not waiting. EV production curves are steepening. Wind turbines are scaling. Precision-guided systems in defense platforms are increasing magnet intensity per unit, not decreasing it. So the gap is not static. It widens quietly through compounding demand and slow-moving supply adjustment. Which brings us to a more uncomfortable realization that rarely gets stated directly in policy language. The question is no longer whether diversification is possible. It's whether it can happen faster than demand intensifies. And on that timeline mismatch, the system starts to look less like a solvable puzzle and more like a race where one side already has a running start. At some point, the conversation about rare earths stops being about geology or even industrial policy. It becomes a timing problem. And timing in global supply chains is often indistinguishable from control. China's position in rare earth magnets doesn't look like a classic monopoly on paper. There are mines elsewhere. There are pilot plants in the United States. Australia ships concentrate. Europe has feasibility studies stacked on feasibility studies. The map looks diversified if you only zoom out far enough. But zoom in, and the structure tightens. Because what matters is not how many dots exist on the map. It's how many of them can consistently produce magnet-grade output at industrial scale without interruptions in quality, environmental compliance shutdowns, or cost spikes that make defense procurement uncomfortable. That's the layer where China's advantage has quietly matured. It's not just that China built capacity. It's that it built capacity early enough to absorb cycles of learning that others never fully ran. Rare earth separation is one of those industries where experience compounds. Each production cycle reduces waste loss rates. Each optimization in solvent recovery improves margins. Each regulatory adaptation stabilizes output. Over decades, that turns into something very hard to replicate quickly, a system that behaves predictably under stress. Now, there's a temptation in Western strategic discourse to frame this as a solvable industrial gap, like building more semiconductor fabs or expanding shipbuilding capacity. But rare earth magnets sit in a slightly different category. They are upstream enough to affect everything, but specialized enough that redundancy is expensive and politically inconvenient to maintain at scale. So countries hedge instead of replace. They build partial alternatives, not full substitution chains. And here's where the strategic discomfort really sits. Hedging works in stable systems. It fails in systems where demand is accelerating faster than capacity diversification. Electric vehicles, grid storage, advanced weapons platforms, they all pull on the same magnetic material base simultaneously. That creates a structural lag. Not a shortage in the dramatic sense, but a persistent friction in procurement cycles, longer lead times, more exceptions, more emergency sourcing. None of it headline-worthy on its own, but collectively it changes who absorbs risk in the system. China, in that configuration, doesn't need to actively weaponize supply. The architecture itself does most of the work. There's also a geopolitical misunderstanding that keeps recurring in commentary. Control over processing does not translate into direct political leverage in a clean, linear way. It is messier than that. It shows up as optionality, the ability to tighten or loosen supply conditions at the margin, the ability to absorb shocks internally while others adjust externally. That asymmetry matters more than explicit restriction. Now, I'm not fully convinced this remains stable indefinitely. The history of concentrated supply chains suggests they always attract countermoves once the dependency becomes too visible. The question is not whether alternatives emerge, they usually do, but whether they arrive with enough depth to matter at peak demand pressure points. And that leads to a prediction that is uncomfortable but hard to ignore. The next decade of rare earth policy won't be defined by new mines or announcements. It will be defined by whether good enough substitutes in performance start entering defense and high-end manufacturing systems, or whether the system quietly accepts higher cost and lower efficiency just to reduce dependence exposure. If substitution succeeds, China's leverage becomes softer, more economic than structural. If it doesn't, then rare earth magnets remain one of those quiet pressure points that never make headlines until something downstream fails. Either way, the assumption that this is a static advantage is already outdated. And maybe that's the real takeaway. Not that China controls rare earth magnets in a simple sense, but that the world built a system where control is embedded in process, not proclamation. If you want to continue this line, we can go deeper into how the US and allies are actually trying to break the refining bottleneck, and why most of those efforts quietly struggle once they hit industrial scale.